So, usually in standard analog circuit, your switch capacitor is used as what? Resistor. Okay. But here in the switch capacitor DC-DC converter, we are basically delivering power to the output. So, we use it as a charge carrier. In the other case also it is a charge carrier, but it behaves like a resistor. Here also each stage will behave like a resistor, but the requirement for that resistor is very small. But if we keep a very high resistor, then we know that losses will be high. So, the difference in standard switch capacitor circuit and DC-DC converter is the power requirements are different. Okay, just like if we were talking about the LC filter. So, in the LC filter path, you cannot basically afford to have large resistor, because conduction losses will be high. But now, same filter, let us say you are designing for any analog signal processing. I want a low pass filter. You do not have as such any current requirement there. Huh? So, you can build with a very large R and small c. So, that is the main difference between the two. So, if let us say I have this VDD, this is my switch, this is C1, this is C2. If this is phi and this is phi bar, they are non-overlapped complementary phases. So, if this is V out, what will be V out after infinite cycles? It will be VDD. Yeah. Every cycle you're taking the charge from VDD and dumping on the output. If you keep doing the for like infinite cycles, ultimately your output has to go to VDD. You do your charge sharing every cycle, you will see your output will keep increasing. Okay. Even though that step will get smaller. So, the first time you do, let us say V out is 0, then you will see it will jump will be large. Then after that smaller because of the charge sharing. Okay. So, this is nothing but same thing, and you will see your relationship will be looking similar like exponential. Okay, because step size is getting smaller, and that is what happens when your output is charged near VDD, it gets slow, it slows down. Huh? So, the same thing happens here also, and this R is 1 over what? Okay. So, which means if I want to reduce R, what do I need to do? Increase the switching frequency or increase the capacitor. So, if I want to deliver, so if I am building a normal RC filter and I do not have any load requirement, then FSW and C1 required may not be that large. But now, if I put a load at V out, then what would happen? So, there is no load. Now, moment I put a load, what will happen? V out will start dropping. Okay, which means you have to charge the output much faster at much faster rate, or your capacitor should have more charge stored in it. So, that is why you have two options, either you basically fill the output much faster or increase the size of your capacitor. So, this is flying cap. So, this is and this guy is storage. You can call it output capacitor also. So, in this case V out equal to VDD, but when we want to regulate the output, we do not want, usually we do not want that. that you can just short V out and VDD. But this just so now if I rearrange the switches everything, that if I want, let us say V out equal to VDD by 2. So, you have to rearrange these switches in such a way that you can get VDD by 2. And there is an analogy also. So, you can think about this is your output cap bucket, big bucket, okay, and these guys are switches actually, they are carriers, and this smaller capacitors you have flying capacitor. So, what you have a source, so this is your VDD and you fill the bucket and you transfer to the next. So, here I have shown only one stage. Now, if let us say I have one more stage, okay, usually depending upon what ratio you require between output and input, your number of stages may be different. So, here it is a boost converter, it is a 3x actually. So, your output will be 3 times of that if you forget about the VT loss here. So, let us say I have a switch here instead of the diode connected device, then you will get 3 times V in or VDD. So, now if I let us say I put a load here, which means I put a tap here and start taking the water out from this bucket. So, it will start emptying. Now, if I rate of the discharge is much faster than rate you are filling, then it will be completely empty. So, which means there is a limit on the load you can put based on what frequency and capacitor size you are putting. So, if I want to increase the load, I have to either increase the frequency, or which means I have to fill this bucket much faster, or I have to increase the size of this bucket if I am filling at the same rate. Okay, and this source is your VDD. So, it has an infinite charge. So, you can keep filling your bucket and transferring into that output. Okay. This was simple, like VDD, V out equal to VDD. So, one important thing you need to remember here, your final output will only depend on flying capacitor, not on the output capacitor. And how you differentiate between flying capacitor and load capacitor? By looking at the circuit, how can we differentiate? No, but if I do not write V out, how will you know which one is connected to output? So, what you need to look like flying capacitor, why do we call it flying? So, this is connecting on both sides. So, it is taking the charge from VDD and dumping to the output capacitor, but if you look at the output capacitor, it is always connected to fixed ground. Okay. So, now if I want to do, let us say VDD V out equal to 2 times VDD. So, I can just simply so if this is called, I will call it now CF, means flying capacitor. This is V out and okay. So, what would happen in this case? Let us see. During phi 1, so phi 1 phi 2 are actually, let me draw here. This is phi and phi bar when I say, or you can call it phi 1 phi 2, whatever, they are actually complementary clocks. So, they should be non overlapped, which means just like we had in gate driver circuit for inductive switching regulator. So, So, they are non why do we need non overlap clock here? So, if both are on, what will happen? The capacitor will be shorted and effective charge will become 0. So, capacitor will fully discharge. So, it will disturb all the equation. So, during phi what is the charge? Or let me write voltage on the capacitor. CF how much? Okay, if I call let us say Vf phi equal to VDD and during phi bar what is? If I call it Vf bar, how much is the voltage? Forget about flying capacitor for now. Sorry, not the output capacitor, C out. Okay. What we are looking at in a steady state, correct? So, what will be the? So, in a steady state, when do you consider this in a steady state? Any switch capacitor circuit, I mean this one or the other one, how will you know whether it is in a steady state or not? So, voltage will not change within that period. So, which means in phi whatever voltage is there in phi bar the voltage will remain same. So, there will be no charge transfer. So, voltage will not change. So, this will be how much? V out, sorry, no, this is connected to where? V out and this is connected to VDD, correct. So, V out minus VDD. Now, Vf phi equal to Vf phi bar, which means VDD equal to V out minus VDD. This implies V out equal to terms of, okay. So, which means I will get output 2x of your input. This is the ideal case. Under no loss, okay. Under loss condition, minus V loss, okay. So, this V loss will be in your switches, mostly in the switches basically this is acting as switch capacitor resistor. So, if you have your capacitor has some ESR, that will also contribute to. So, any resistive losses basically you know its conduction losses. So, that will contribute to V loss which is in the conduction path. So, IR drop will be there and V loss is proportional to I load. Phi 1? Oh, this is complementary actually, usually use complementary switches. So, let me do one thing. So, you can maybe make phi bar inverted or put an inverter on the other side. So, let me fix it. No, yeah, correct. So, what would happen? So, if it is a, let us say one is PMOS, one switch is PMOS, other is NMOS, then it will be exactly same what we had. So, we are more used to of having the P and N in switching regulator. So, that is why. So what would happen? This will turn off and okay. So how do we regulate the output? Everything is open loop. Now your load is changing. So let's say I want two VDDs. I cannot even regulate 2 VDD because under load conditions, your load is varying, your output will vary. So how do we regulate? Or let's say my input is 2 volt and I want output 3.5 volt. So it's a 1.75 times your gain ratio basically required here. So it will not regulate. Okay. Is there any way I can regulate the output still by keeping, let's say, 2 VDD? So obviously in under load condition you cannot get. So the ideal condition is a 2 VDD, which means you will always get below 2 VDD even if you try to regulate it somehow. Let's say I required 1.5x, then you will choose 2 VDD. So but how will we regulate at 1.5x? So there are some applications where you want you don't want to regulate the output, but you may still want 2 VDD or VDD by 2 fixed ratios. Okay. So let's say I want to boost my output voltage from 2 volt to 5 volt. Okay. So one way would be okay, you just have a switching regulator and based on what ratio you require, you can choose the duty cycle. It's straightforward. Okay. So 50% it will give you 2x, here 2.5 times, so slightly more than 50% will give you that. Okay. So another application, let's say I want 1.5x. So one possibility would be you do a 2x from the charge pump and put a buck after that, and it will give you 1.5. And if you guys remember that what is the problem in the boost, it's a bit slower because of right half plane 0. In this case you can easily get rid of that right half plane 0. So that's a one application. Now let's take case of buck converter. So let's say I want to regulate the output at 1 volt and my input is 10 volt. So what is your duty cycle required? 10%, which is almost at the border, lower side. You hardly have any room to respond to transient. Okay. So duty cycle is almost saturated. So what you do divide by 2 from charge pump. So 10 volt become 5 volt, and now from there you with a 20% roughly duty cycle you can get 1 volt output. Okay. So in open loop these are the applications, but sometimes we use in the closed loop also these, and we can regulate the output.